Hi and welcome to this tutorial on hydrogen bonding in water. In the previous tutorial, we learnt about intermolecular forces. So we looked at London forces, we looked at permanent dipole-dipole forces and hydrogen bonding too. And we also learnt how intermolecular forces can influence the physical properties of a compound, such as boiling and melting points. In this tutorial, we are going to be looking at boiling and melting points in more detail, surface tension, viscosity, density, and water as a solvent. So all of these in relation to water. A recap, remember that hydrogen bonding is a special type of intermolecular force, okay? Well, it's a special type of permanent dipole force, technically, but it comes under the intermolecular forces bracket, and it forms when we've got a hydrogen atom that's covalently bonded to a very electronegative other atom, and that other atom has to be N, O, or F. And that other atom has to have a lone pair available on it. And the hydrogen atom also has to be electron deficient, effectively. So if we had an alcohol here, so R means it could be anything. And then I've got a group there. And then I had another group here. Then we've got that electronegativity going on because of this polar bond. On both, so I'm going to add my dipoles in. I'm going to add my lone pairs in because the N or the O or the F, the O in this case has to have a lone pair, and that's where we get our hydrogen bonds forming between the electron deficient hydrogen here and the lone pair on the oxygen over here. And of course, in an exam, I would have to label that bond as a hydrogen bond to make that really, really clear to the examiner. And I just gave you an example of an alcohol, but of course, water is able to hydrogen bond because we've got an O and an H and we've got another O and an H here. Water is a highly polarized molecule and it can form an extensive hydrogen bonding network because it can effectively, each molecule can form 4 different hydrogen bonds. We can have one coming off from each hydrogen, and then we can have 2 coming off because we've got 2 lone pairs available as well. So the lone pairs of electrons on the oxygen atom are going to be attracted to the delta positive of another hydrogen nearby, effectively, as you can see in this particular case here. So there's my lone pair, and it's attracted to the partial positive charge on the hydrogen of a nearby water molecule. Okay, and the extensive hydrogen bonding that occurs in water accounts for some of its anomalous physical properties that make it particularly good for life surviving, for example. So it's a big part of biology. We can see it in its boiling and melting point. Surface tensions, we know we've got pond skaters can walk on the surface of water. Its viscosity and its density too. So the fact that ice is less dense than liquid water, that's something very unique to water. So we're going to look at these in more detail. So here are 4 things that we're looking at. So boiling and melting point, surface tension, viscosity, and density. We need to be able to use our information about hydrogen bonding in water to explain all of these anomalies. So looking at the group 6 hydrides. So I've taken my group 6 and bonding them with 2 hydrogens, group 6 hydrides. The boiling point of water is much higher than the rest of the pattern. So it's much higher than expected. And the same pattern is seen for melting points too. And it's all to do with the fact that our molecules here, we've got an increase in the strength of the London forces as we move down the group of group 6 because the molecules got more electrons, they're getting bigger. Okay, but our red oval is circling water here. It's because water can form hydrogen bonds and the other molecules cannot form hydrogen bonds because it's not N, O, or F. We've got an oxygen here with a lone pair. So these hydrogen bonds are obviously the strongest type of intermolecular force, and so they require the most energy to overcome and break, hence the high boiling point. We've got surface tension to discuss. So it's a measure of how strongly molecules are held together on the surface of a liquid. And water has a high surface tension. It's because often at the interchange between the air and the water, we get the strongest hydrogen bond on the surface parts, which requires more information to explain. You can look that up if you want. And the hydrogen bonds exert that strong downward force on the water molecules at the surface. Then we've got viscosity. So that's a measure of how resistant to flow a liquid is as a result of the friction between its molecules. So something that's really viscous would be tar, and water in comparison to tar is obviously not very viscous, but actually in comparison to a lot of other molecules, it's got some very interesting properties and it actually has got high viscosity, which is a bit hard to consider and imagine. And the reason why is hydrogen bonds between the water molecules make them less capable of sliding over each other. So water has got a higher viscosity compared to other molecules of a similar size. And then we've got the idea of density. So we know that water exists in a liquid state at room temperature and pressure. The molecules are moving closely together if it's in a liquid state, but they're not in a regular lattice structure. When water freezes, we are going to get more of the hydrogen bonds being formed. In liquid water, there are 4 possible hydrogen bonds that can form from each water molecule, but not all 4 are formed. There's too much energy, the molecules are moving around too much. It's in a dynamic state. Those hydrogen bonds are constantly breaking, reforming, breaking, reforming, breaking, reforming. If you lower the temperature of the system down and down and down, and as you approach 0, the molecules will move around less and less and less. And eventually, they will move so little that all 4 hydrogen bonds will be able to form, or near enough. And so we will form a lattice effect, a lattice structure. And those hydrogen bonds are going to hold all of those water molecules in that fixed regular lattice, but it actually holds them quite far apart, which is what creates the lower density of solid water compared to liquid water. There's lots of air. There's less particles per unit volume. And you can see that in the image down here. There are 4 hydrogen bonds being formed, and it's holding the molecules further apart than they are in the liquid. So ice is less dense. And that's a huge part of what supports life on Earth. And so I was just discussing this. We've got an open structure of ice. This figure shows the water molecules are further apart from each other than they are in liquid water. So solid water, they're further apart, or ice. And this gives the open structure and makes it less dense. And of course, water is a solvent, again, essential for biological life on Earth. Most of our bodies are made of water, and it's all to do with all of the minerals, and everything we need is dissolved in that water. So when a compound dissolves, there are intermolecular forces within the compound that have to be broken, and new bonds between that solute and the solvent have to form. Okay, so the types of new bonds that the solvent can form depends on whether the solvent is polar, so has permanent dipoles on its structure, or non-polar, so non-permanent dipoles. So for example, diether. A polar solvent would be something like water. Go back a few tutorials back if you want to have a look at the difference between polar and non-polar molecules, if you need a recap of that. And for a solvent to be able to dissolve a compound, both have to be able to form similar intermolecular forces. Like dissolves like. So polar solvents dissolve polar compounds, and non-polar solvents will dissolve non-polar compounds. Non-polar solvents will not dissolve polar. Opposites do not dissolve in this particular case. So water as a solvent, it's going to be dissolving mostly polar compounds because it's polar itself. So here's a summary. We've got water can dissolve ionic compounds. Water can dissolve simple alcohols, as long as they don't have a long hydrocarbon chain, because they're obviously very non-polar, and water's a polar solvent. All polar compounds dissolve in water. Water does not dissolve non-polar compounds. So here we've got our water dissolving ionic compounds. So the partial charges in the water mean that the water molecules are going to reorientate themselves facing the opposite charge. So the oxygen is partially negatively charged, so it's going to be attracted to the positive ions in the ionic lattice, and vice versa. The hydrogen with the partial positive charge is going to be attracted to the negative ions in the lattice. And so they're going to be able to break up these ionic bonds, and these ions are going to be more interested in engaging with the water molecules. So it's going to solvate the ionic lattice. So the strength of the ion dipole interactions is enough to overcome the ionic bonds in the lattice and break them up. You can see these water molecules are pretty much pulling them away. And then we're going to end up with water molecules surrounding each of these ions. As you can see in this image here, they're solvated. So the dissociated ions that have now been pulled out of the lattice become surrounded by the water molecules. It's known as hydration or solvation. And the water molecules will orientate themselves according to the charges. So you can see that the partial positive hydrogens are going to be attracted to the negative chlorines. That's why the water molecules orientate them this way, and they orientate themselves in the opposite direction with the positive cation. And as I said before, water can dissolve simple alcohols. So as long as we don't have a really long chain of non-polar hydrocarbons, it will be able to dissolve the alcohols. And we know this with ethanol, for example. We can definitely dissolve that because, with alcoholic beverages, etc. And the longer the carbon chain in the alcohol it is, the less soluble in water it is, because the London forces are going to be stronger. They're not going to be able to be overcome by water's polarity and trying to form those polar bonds. And you can see here a hydrogen bond that has been formed. So a hydrogen bond, and it's going to be able to surround the molecule. And then we've got the idea that not all polar compounds dissolve in water, though, so it's not a guarantee. So haloalkanes are insoluble in water. Okay, so here is an example of a haloalkane. So it's an alkane, but with one of the hydrogens replaced with a halogen, a group 7. And their dipole moment is too weak, okay, for hydrogen bonds to form within the water molecule. So what we don't have in terms of this molecule here are hydrogen on our oxygen. It's not going to be able to form that hydrogen bond there, so we're not going to be able to dissolve it. And water does not dissolve non-polar compounds, so only non-polar solvents can dissolve non-polar compounds. The phrase like dissolves like is helpful to remember here.